Hello everybody, welcome to Chapter 7 on the sampling distribution of the sample mean. This section is really a continuation of what we did in Chapter 6, talking about the normal distribution. The difference in this case is that we're now taking what we've learned from our probability in Chapter 5 and the normal distribution and probabilities in Chapter 6 and talking about distributions of samples. And what could we say about samples as opposed to just single values chosen from a distribution and say what happens when we take a sample from that population? What could we say? So the first thing we want to talk about is something called the sampling distribution of the sample mean. And we really get into the topic called sampling error and the need for sampling distributions. Remember that when we are busy trying to find out some information about a population, the way we deal with that population is by looking at a sample. Really, our only choice is to deal with a sample. So the question for us is, how can we assure ourselves that we get a sample that actually reflects the population as a whole? And how can we ensure that our sample is going to be within a normal distribution? That's important for us because we're going to base our conclusions, our inferences about those population samples on what our population distribution says. So that's where we're at with this one. And so the first term you have to know here is called the sampling error. And the sampling error is what we say is the error that results from using a sample to estimate a population characteristic. So let's say that we're interested in mean heights. Population characteristic is the height, and we're looking for a sample to estimate what we could find out about the entire population as a whole. What could we say if we took a sample of 1,000 men and found the average height, the mean height of those men, and how would that reflect accurately or not the population height as a whole? The other term that we have to know is called the sampling distribution of a sample mean. And for a variable x and a given sample size, the distribution of the variable x bar, that is, the distribution of our sample means, we use x bar to represent our sample mean, you call that the sampling distribution of the sample mean. And probably the best way to describe this is to use an example, and this is actually problem number 1 from our handout. The possible samples and means for a sample of size 2 are chosen. Let's make it really easy, because it gets to be very difficult if we're talking about very large populations. So for the illustration in this case, let's take a population of 5 basketball players. Okay, so here are their heights in inches. 76 inches is player A, 78 inches for player B, 79 for player C, 81 for player D, and 86 inches is player E. And what we want to do is we want to see, well, what would it look like if we just started taking samples of this population? And so we're going to make it a really small sample. Now, again, please be aware that this is a very small and limited population and a distribution size. However, the job here for us is not to worry so much about having a big or small population, but really just based on the population that we have at hand, that is our 5 players, what could we say about the mean of our samples? In other words, if we took samples of size 2, what could we say about the mean of the sample of each of the samples? So that's what we've done right here. We say, okay, well, let's just systematically go through and find all of the possible samples of size 2 that we can from this population of size 5. So here they are. There are 10 possible samples of size 2 that we could take from a population of size 5. And we see that, for example, right here, players A and B are chosen. Their mean height is 77 inches. If players A and C are chosen, their mean height is 77.5 inches. For A and D, the mean height is 78.5 inches. And on down the line, you can see that we've done that for each of these. So what could we say about each of these sample heights? Well, this is an interesting question because, okay, none of the sample means are the same. So how could we say anything? What conclusion could we reach about the sample mean? Well, I would be interested in finding out what is the mean of each of these samples right here. If you actually went into your computer right now in Excel and entered in all of these heights, all of these mean heights, and you took the average of them, what would you find? Well, amazingly, what you would find is that the average is actually 80 inches. And I'm going to go ahead and I'm going to bring up my Excel spreadsheet to show you this. So I have our mean heights right here, right? Here's the means. So what I'm going to do right here is I would go through and I could find the mean of each of these guys right here. And so I'm going to get equals average. And let's go ahead and take the mean of those averages. 80 inches. There it is. Oh my gosh. Yes, that's exactly the same as the mean height of the entire population. If you added 76 plus 78 plus 79 plus 81 plus 86, we're going to get exactly 80. How's that for amazing? Yes, it turns out that every single time we take a sample, if we could get every possible sample of whatever size from a population, and we could check all of their means, it always happens this way. Now, isn't that amazing? All right, so now that we know that, let's talk about that sampling error, what we call a standard error. And I'll show you how I do this here manually. Now, you guys can copy along using Excel. So what you're going to do is you're going to enter in your heights. And so we have our heights for our samples, A and B, 76, and I took their mean. And the mean of the population is 80. So what I did was that I said, let's subtract 77 minus 80, which is the population mean, and square that. And then do that all the way down the list here. Whoops. No, that's not what I wanted to do there. There we go. Okay. I wanted to go down the list right there. And look. Okay, so we take the difference between 77 and 80 and square it. Well, that's 3 squared. That's 9. We take the difference between 77.5 and 80 and we square that. 6.25. 2.25 for the square of the next one. 1. Right? 1, because 81 and 80 is difference of 1. 1 squared is 1. And we go all the way down the list doing that. Now, if you recall, we have a formula for the standard deviation. And in fact, what we're doing is just like in the bowling thing, we're doing our standard deviation. And our standard deviation is going to be the sum of the square of the difference between each mean and the population mean. That's what we see over here in the right column. And we take that sum, divide it by the sample size, since this is all of the possible samples, this is the entire population of our samples. So we're going to take this sum and we're going to divide it by 10, pardon me, and then take its square root. And this is our standard error. In fact, this standard error can sometimes be referred to as the sampling distribution of the sample mean, right? So right here, this is what you guys are going to do in the assignment. You're going to get those sample means that I just did in our table, and you're going to fill in this table, and you can copy it over from Excel into Word and get this table. So what observations can we reach about this particular situation? Well, on the handout I ask, if we're looking at if we want to make some observations about the sampling error when the mean of the height of a random sample of 2 players is used to estimate the population mean, well, we can see that we get a pretty large variation. But the mean variation, right, the mean variation, I guess our standard deviation of each of these population means, each of these sample means is 2.08, about 2.1. So if we look over here and we go to about 2.1 on our board and just mark that out, let's see, 2.1, let's see, that's 81, 2.1, and a 2.1 right here, right? This is 1 standard deviation away from the mean. Remember our empirical rule? Here it is, right? all of our means, almost all of them, with the exception of 2 on the left and 2 on the right, are within 1 standard deviation of the mean. If we went 2 standard deviations of the mean, 95%, well, all of our samples are within that height, right? So that's pretty good, right? We can make some observations about the sampling error, basically. Based on this diagram right here, we can see that the dot plot shows us that most all of the observations of our sample mean are well within 1 standard deviation of that mean. Now, for the probability that a random sample of size 2, the sampling error is made, let's see. Find the probability that for a random sample of size 2, the sampling error made in estimating the population mean will be within 1 inch or less. So let's see, we had 10 observations, that's 10 samples. And so what we're going to do right here is we're going to go 1 inch to the left and 1 inch to the right. And we've got that one at 81, so we'll include that in. So what is our probability that for a sample size 2, the sampling error made will be within 1 inch or less of determining the probability, right? Well, let's see, that means that for us, we have 3 within 1 inch, and that's out of 10. So the probability that our random sample of size 2 has a sampling error within 1 inch of the mean. Well, that's pretty good, right? So we know that we have a 3 in 10 chance, a 0.3 probability of getting within 1 inch of the mean if we take a sample of size 2. So that's an interesting question for us. Here's one. What happens if we do it with 3? Well, okay, let's run through the list right here, right? This time we look to see, well, what could we do about getting samples of size 3? Will things improve or will things get worse? Well, what we're going to do then is we're going to take our samples, A, B, and C, of each of our players right here, samples of size 3. So we go down and systematically see that the samples consist of players A, B, and C, A, B, and D, A, B, and E, A, C, and D, and A, C, and E, and then A, D, and E, right? And we look at this, there's a total of 10 possible samples right here. So I did the same thing that we were just talking about before in Excel, and you should do this as well. I'm going to post this sheet that you guys can fill in yourselves right here. But what I did was I took our mean for each of these guys right here. There we go. And I see that the means are 77.67, 78.3, 80, 78.67, and so on down the list. And I see that our means are pretty close, right? It's kind of like what we had last time, but let's see about that standard deviation, and let's see what kind of observations we can make here. So I took the difference between that mean and the population mean of 80, and I squared the value, and then I found my standard deviation. And here it is, my standard error is now 1.39. Notice that before my standard 2.08 or 2.09, now it's 1.39. It's a little bit closer. That's sort of interesting. So what does that mean to us? Well, if we're going to go through and we're going to get our sampling error right here, we can make some observations and compare it to what happened with 2. Remember that we said that before, right, when we had a sample of size 2, these samples were kind of spread out, right? We were, let's see, we had 2 observations within a standard deviation, right? 2 standard. Now, let's take a look right here. 1.39, right? That's our standard deviation. We still have the same observation about that, right? Our standard deviation was 1.39. So, whoa, let me get my pen working. Come on, pen. 1.39 of the mean, right? So 1.39 right here, 1.39 this way. We see, well, pretty much the same thing that we saw before. 67% of our observations were within 1 standard deviation of the mean, right? There were 2 observations that were outside of that, but none that were outside of 2 standard deviations of the mean. Right? And so we can say that it looks like our observations are repeating what happened when we took a sample of size 2. We get one standard deviation, except that that standard deviation, which we call our standard error, is now closer to the mean. But now let's look at our probability here. What is our probability that we're going to get what for a sample of size 3 that the sample mean will be within 1 inch? Well, all right, now let's try it. 79 inches here, 81 inches here. We've actually got 2 observations that fall within that. So now we've got 1, 2, 3, 4, 5 observations out of the 10 observations that are within 1 inch. Now that's actually very interesting, right? It seems as though by increasing our sample size, we've increased the probability that our mean sample height is going to be within 1 inch of that mean. Well, that's pretty good, right? That means that our population mean, which is 80 inches, we've increased the probability of getting a mean that is close within 1 inch of that standard standard deviation of a mean, right? Within 1 inch of the mean, really. That will be 1 inch or less. And that's pretty good, right? And what would happen if we kept on increasing this sample size? Well, pretty much what you would expect. As we increase the sample size to more than 3, right? So here was our sample size of 3. If we take a sample of size 4, almost all of our samples are within 1 inch. And of course, sample size 5, that's the entire population. That is a mean of 80, right? So what happens is that the way the values of our means are distributed decrease. And amazingly, this happens with every single kind of sample and population mean that you can imagine. So the long and short of it here is that when we're looking at our sampling distributions of the sample mean, there's some things that we can definitely come to a conclusion about, right? The sample size, as the sample size goes up, the number of possible samples that we could get may change, but the number within 1 inch, look at this, right? We went from 3/10 to 5/10 in this case, right? If we went to a size 4, then 4/5 of all of our samples were within 1 inch, right? And so that probability increases as we go along, right? And that is really a very important thing. So based on our observations from the tables above, what's the relationship between the sample size and the sampling error of the mean? Well, as the sample size goes up, right, we could say that as the sample size increases, let's see if I can write, as the sample size increases, there we go. As the sample size increases, our standard error decreases. And that's an amazing and important point, because now we actually have a relationship between the way that we take a sample and the way that we're actually going to be able to find the mean of our samples. And we can use that as a way to help us figure out what we're going to talk about with those samples. So the sample size is, as the sampling error says, the larger the sample size, the smaller the sampling error tends to be in estimating the population mean by using a sample mean. So we'll talk more about this fact in the next video.